16.1 Dilations. Some vocabulary. Transformation. A transformation is a change in position. That means we're moving our object. A reflection, a rotation, or a translation are all examples of a transformation. You know reflections. Reflections, when your shape is reflected across a line of symmetry. You can see this white line here, and now you can see that the rose is above the line and below the line in the water. This is a reflection. A translation would be when an object moves, kind of like what this hexagon is doing here. It's skateboarding and it's moving itself this way to the right. A rotation are when things move around in a circle. So this is a rotation. You have a point of rotation in the center, and you would have an item, like for example this blue would move here and here and here and here and so on until it goes all the way around as a circle. You can move around in different degrees. So for example, I could just move 90 degrees, that would be here, or I could just move from here 30 degrees, which would be about there. Also, if you stare at this picture long enough, you can see that your eyes are tricking you and it looks like the circles are moving, when in reality you and I both know that they're not moving. A dilation is another type of transformation, so a change in position where the shape is made larger. So if you see here the reflections, the translations, and the rotations, those move, but the shape stays the same size. This hexagon moved, but it stayed the same size. These circles moved or went around, but the shapes themselves, the little ovals, stayed the same size all the way throughout the circle. In a dilation, what happens is that once you move your shape, it becomes larger, or it could become smaller without changing its position or direction. Okay, let's talk about what a scale factor is. So a scale factor is a ratio, which another word for a ratio is a fraction, that expresses the amount of a magnification. So you can see in this picture here that we have an Lamborghini Aventador AE2, and there's a tiny model and then there's a larger scale model. This is not the life size, but it's very close to life size. But you can see that the small car was magnified and it became larger. So in order to show how much larger it became, we're going to need a ratio or a fraction in order to express the amount of the magnification. Okay, another way of looking at a scale factor is going to be the ratio, which again is a fraction, of any two corresponding sides. Now, if you remember from earlier, corresponding means that we're going to be looking at two sides that are in the same position. So for example, on these cars, I'm not going to compare the front of the car with the side of the car here. Those would not be corresponding. If I'm going to compare the side, I'm going to compare the side and I'm going to compare the same side. So for example, this is the passenger side. I'm going to compare that to the passenger side. That would be corresponding. Or the front of the car with the front of the car. That would be corresponding again. The ratio must be reduced to the lowest terms in order for it to be considered a scale factor. So, you know, sometimes you're looking at shapes and you have numbers and you set up a ratio, you set up some type of a fraction. But if that fraction is not reduced, then it won't be considered a scale factor. In order for it to be considered a scale factor, it must be reduced to lowest terms, the lowest terms possible. Okay, so if you can see here, I marked in red here what I'm going to check a measurement on. Now, I actually do not know the actual measurement, so I'm going to write in some numbers so that we can work on finding a scale factor. I'm just making these numbers up, but let's pretend that For every 6 inches on the small car, I have an 8 actual inches in the real life size version. So again, and if we go backwards, for every 8 inches that I see here, I'm going to translate that into 6 inches back into the smaller car. So in order for us to find a scale factor, you would need to know if you're going from the smallest to the biggest car or from the biggest to the smallest car, and most problems will actually mention that. So let's write that down. We're going to write that down. So let's go from the larger car. Let's go from the larger car down to the smaller car. So we'll do a ratio from the larger to the smaller. Okay, so it'll be 8 will go on the top of the fraction. And since it's a fraction, I need a division line. And 6 will go on the bottom of the fraction. Now this at this point is just a ratio, but it's not a scale factor at this point, because we can actually reduce the fraction. So both numbers can be divided by at the most 2. So we're going to do that. And once I divide them both, I'm going to get 4/3. Now this is actually our scale factor. So what does this mean for us? So I'll put that in blue right next to our previous numbers. So let's look at that. And we'll see that the 8 reduced to an actual 4 and the 6 reduced to a 3. So in reality, what they're saying here is that for every 3 inches in the small car, you have 4 inches in the larger car. Same goes for going from the larger to the smaller. For every 4 inches that you have on the larger car, it translates into having 3 inches on the smaller car. So you can think of this like when you were doing maps in geography. You had a little key where it said 1 centimeter, and then in real life it's really like 4 miles. So those would be considered scale factors. All right, so let's look at our images here, and let's learn how to actually show how to say or name the shapes. So in this first example here, we have a penguin. We have 2 penguins. And we can see here that this is a dilation, obviously, because the size changes. So anytime the size changes, we're going to have a dilation. This is what we call a contraction in math, or a reduction, because the pre-image is larger than the image. The image is what happens to the shape after we've done the dilation. So we started off with the large image, we did a dilation which shrunk our shape, and now we get our image. So the pre-image is the original, the image is after the dilation. Let's take a look at what happens with this rectangle down here. I have a rectangle A, B, C, D. And you can tell that my original rectangle is a lot larger than my image. Now, you can tell that this is the actual pre-image because there are no tick marks above the letters. And they're actually not called tick marks. If I want to name this shape, it's called A prime, B prime, C prime, and D prime. And I go around in a circle. A prime, B prime, C prime, D prime. And I wrote it here for you. A prime, B prime, C prime, D prime. But when you write it like this. All the letters in a row with the tally right above on each one. So I know this second rectangle is my image. Because it has the primes on it, so that's my image, and my original, which does not have the primes, is my pre-image. So this is rectangle A, B, C, D. Once it was dilated or reduced, then it became rectangle A prime, B prime, C prime, D prime. For our second type of dilation, this is an expansion or an enlargement. So you'll see either word, expand or enlarge. Our pre-image is actually smaller. This is our original shape. And after the dilation, it enlarged and it became very much larger than the original. And this is the image. So you can see here that I have rectangle JKLM, and it becomes, after the enlargement, after the dilation, it becomes J prime, K prime, L prime, M prime. On this page, I'm going to help you with the explore part at the beginning of your lesson. So let's discuss that. We can see here that they talk about a dilation being a transformation again, which is a movement, and that it can change the size, which we talked about earlier, but it has to leave the shape unchanged. So in other words, it has to be the same direction. It has to be pointing in the same direction. A dilation has a center of dilation. The center of dilation will be a point that we're going to be referring to. And the scale factor we talked about, it's a fraction that it explains the enlargement or the reduction, and which together determine the position and the size of the image of the figure after it's been dilated. So let's take a look at our triangles here. They're going to use triangle ABC. That's this first triangle. And its image. So this must be the pre-image. So let's write that down. So you can see here that I've written down which one was the image and which one was the pre-image. So our first one, triangle ABC, is our pre-image. And after it's been dilated, we have triangle A prime, B prime, C prime. And now we have some questions to answer. So, well, obviously for part A, you're going to need to use a ruler in order to measure all the lengths. So you're going to need to use a ruler to measure from A to B using centimeters. Then you're going to need to use the ruler from A to C using centimeters again. And then from B to C again using centimeters. And all of them are centimeters. So A prime to B prime, A prime to C prime, and B prime to C prime. So, and the measurements are already written down for you, but I would still use a ruler just to check to make sure I know how to use my ruler, or to practice using my ruler. Okay, using a protractor, you're going to need to measure the corresponding angles. So again, corresponding means that they are in the same position. In other words, we're looking at them being in the same place. So angle A is corresponding with angle A prime. Angle B corresponds with B prime. And angle C corresponds with C prime. Now, if you notice, after they've used the protractor, angle A measures 22. What does angle A prime measure? Also 22. Angle B measures 33. Angle B prime also measures 33. Angle C, which is this angle, measures 125. And angle C prime also measures 125. So even though our actual shape looks, our image looks smaller than our pre-image, so our shape changed in size, however, the angle measures, you can tell, are actually staying the same. But when you look at the size of the sides got smaller. So our shape actually got smaller, but our angle measure stayed the same. That's going to be important. Now they want you to complete the following ratios. And remember that ratios are actually fractions. So that's why all of your answers look like fractions. So let's talk about which ratios they want. They want to know what A prime, B prime is. So A prime, B prime measures 3 centimeters, so 3.0. AB measures 6 centimeters, so 6.0. Now that's the same thing as 3 over 6. And both of my numbers there can be divided by 3. So I'm going to divide by 3 on both of them. And that's how we're ending up with 3 divided by 3 is 1. And 6 divided by 3 gives us 1. And 6 divided by 2 gives us, 6 divided by 3 gives us 2. And you can see here that we're getting a fraction as our answer, which is a 1/2. Now they want the measure of A prime B, A prime C prime. So A prime C prime is 2 and AC is 4. So 2 over 4 is the same thing as 1/2 by the same reasoning here, except here I would divide by 2 on both of them. So if I divide by 2 and I divide by 2, then I'm ending up with 2 divided by 2 is 1, and 4 divided by 2 is giving us 2. So we're getting 1/2. B prime C prime. B prime C prime is 1.5, and BC, which is the bottom, is giving us 3. So this is 1.5 divided by 3. Now, if you divided them both by 1.5, that's how they're getting the, so divide both of them by 1.5. Think of $1.50. There's $1.50 in the 3. So divide them both by $1.50. There is, if I divide $1.50 divided by $1.50, I get 1. And $3 divided by $1.50, there's 2 $1.50s in $3, so that's a 2. So we're getting 1/2. Now, if you were to have done this all on the calculator, for this problem, you would have gotten 0.5. For this problem, when you divided 2 divided by 4, you would have gotten 0.5 on the calculator. If you would have done 1.5 divided by 3.0, then you would have gotten 0.5. So you can do this also. You can check with your calculator to see if you're getting the same ratio every time. Now, these ratios, because I'm getting the same number every single time and it's reduced to lowest terms, that means that our scale factor in this case, because we learned scale factor earlier with the Lamborghini, is going to equal to 1/2. And that would be your scale factor for this problem because it's reduced to lowest terms. See, here I have a fraction, but it's not lowest terms. Here I have another fraction, but it's not lowest terms. And here I have another fraction, but again, it's not lowest terms. So our scale factor is 1/2. Okay, let's discuss what we noticed here. So it says to reflect. What do you notice about the corresponding sides of the figure? The sides that are in the same position. For example, AB corresponds with A prime B prime. What did you notice about their measures? What do you notice about the corresponding angles? So when we talked about angle A and angle A prime, what did you notice about those angles? So here's the answer. The ratios, the fractions of the lengths of the corresponding sides are equal. So these fractions here are equal. And the corresponding angles are congruent. So the corresponding angles are congruent because the measures of the corresponding angles are the same. But the ratios, so the ratios of the corresponding lengths are all equal. Now sometimes we call that proportional. I know you haven't heard that in a while, but if I said basically 3 over 6 equal to 2 over 4 equal to 1.5 divided by 3, I'm getting all the same answer, which is 1/2, which when fractions are equal, we call it being proportional. I don't think I spelled that right, so let me fix that for you. Okay, so I'm going to rewrite that for you. Proportional. There you go. That's much better. So you can see here that 3 over 6 is the same as 2 over 4 is the same as 1.5 over 3, which is all equal to 1/2. That means they are proportional. Let's go to our discussion. What similarities are there between reflections, translations, rotations, and dilations? And what are the differences? So if we remember, reflections was the rows, translation was the little hexagon that was on the skateboard, rotations was that that shape that was moving or tricking our minds, that optical illusion that we saw, And the dilations are when we make them grow or reduce, which is shrink. And then what is the difference? So reflections, translations, rotations, and dilations all are going to preserve the angle measures. So no matter what you do, you make it bigger or smaller, the angle measures are going to be the same. So that's very important. It's going to preserve angle measures. That's what makes them the same. Now let's talk about what would make them different. So let's talk about that, and I'll change colors here. We'll go to green. Okay, so what makes them different? Reflections, translations, and rotations are all preserving distance, but dilations do not preserve distance. That means that our shape is getting bigger or smaller, which means that the distance between one vertex to another is changing. So that's where our differences are. So dilations do not preserve distance, okay? So obviously this is what makes them the same, and this is what makes them different from each other. It's very important that you know what's making them the same or different. It's very important that you make comparisons. This slide shows you some properties of dilation. So let's talk about those properties. The first one is dilations preserve angle measures. That means your angles are going to be congruent. Dilations preserve betweenness. So there's a formula to find out if your dilation is preserving betweenness. And what you would do is you would take the measurement of AB plus the measure and take the absolute value, which is going to be a positive number, plus BC, and then you take the absolute value of that measurement, and if you add them together, should equal the measurement of A prime, C prime, if you take the absolute value of that side too. So that'll help you find out if it's preserving betweenness. Okay, dilations preserve collinearity. So that means collinearity is when three or more points are on the same line. For example, you would have A prime, and the center of dilation all on the same line. That would mean that they're collinear. Okay, number 4, dilations preserve orientation. So that means that when you are done making your shape become bigger or smaller, that it should be facing in the same direction you started in. If not, then it's not preserving the orientation. Okay, and number 5, dilations map a line segment to another line segment whose length is the product of the scale factor and the length of the pre-image. So basically, if I have a measurement of, let's say, one shape, if I multiply, so this is multiply product, if I multiply by the scale factor, so I find out the measurement of this segment here, and let's say the segment is 2, okay? And let's say my scale factor is 5, for example. Then 2 times 5 would give me now a segment length that measures 10. So, and that's just a simple example. So this is just saying that if you take your pre-image and you multiply it by the scale factor, you will have your new length, which would be 10. Now, obviously, if we are reducing, then you're not going to multiply by the scale factor, you would divide. So, for example, if I started off with 10 and I'm making my shape smaller, then I would divide by 5, and then I would get a shape of 2. So I started off with 10, I made it smaller into 2. Again, if I started off with 2, I make it bigger by multiplying, and I get 10. So back and forth. Okay, number 6. Number 6 says that a dilation will map a line not passing through the center of dilation to a parallel line and leave a line passing through the center unchanged. So that means that if I'm able to draw another line and that line is parallel, then the center has not changed, it's still the center, then that means that this would be a dilation. Okay, some things that the book did not mention that I think are good for you to know and to have on this list is that if you are making your shape bigger, you're doing an enlargement, then K, where K is the scale factor. Now remember, that's a fraction. You know, it could just be a whole number like 5 earlier, but 5 can be turned into a fraction, 5/1. So it's still a ratio, still a fraction. So K is your scale factor, okay? If you find out that your scale factor, you take the absolute value of it. If after taking the absolute value, it's bigger than 1, then this would be an enlargement. Also for a reduction, if you have that fraction, that K, and you take the absolute value of that fraction, and you find out that even after you've already taken the absolute value, that it's a number less than 1, for example, 1/2, then you know that this is a reduction. All right, number 8, another thing that the book didn't mention on this list. It mentioned it earlier on one of the reflect questions, but it's not on this list. Your corresponding side lengths ratios, which are not your scale factor because your scale factor is reduced to lowest terms, but when you are doing the corresponding side lengths, like for example on the Lamborghini, when I started off with 8/6, it wasn't a scale factor yet, but it was the corresponding side length ratio. It was a fraction, and I did do corresponding sides because they were in the same position. Now, if I do all of my side lengths and I set up fractions, my fractions need to be proportional. Now, that means that all of my fractions will equal each other. So that's another property of the dilation, is that the side lengths are not necessarily going to be congruent. They will be proportional. Proportional is different than congruent. All right, so there's your list. Okay, I'm going to work with you on example number 1. So basically what's happening here is that we're going to see the angle measures and see if they're getting preserved. So you can see here that angle A prime and A measure the same. Angle D and D prime measure the same. Angle C and C prime also, and B prime. So yes, it is preserving angle measure. Now, between this, earlier we talked about the absolute value of AB plus the absolute value of AC is equal to the absolute value of A prime C prime. Now, this is not actually literally a formula, but basically if you see here, I have 3 spaces, so 1.5 would be my halfway point. So really what they're saying is that if I were to use that as my center of dilation, then if I measure from that point to A and from A to D, that it would be the same thing as if I was measuring from here, from the point all the way to D, so from here to here. So that is betweenness. So yes, there is betweenness. Now as far as collinearity, yes, there is collinearity. D prime, A, and D are all on the same line. C prime, B, and C are all on the same line. However, there's no orientation. So you can see here that there's no orientation because the shape used to, the A used to face to the left, whereas now the A prime is facing to the right. So you can see now that the orientation has changed, where it used to be, if I draw this shape just the same way over here, it should look like that, and it's not anymore. So I drew it for you in a different color so that it's lighter to see. You can see here that the shape was yellow, and if I drew it over here, it would be facing in a different direction. So no, it is not preserving the orientation. Also, the ratio to the corresponding sides is 1 to 1, so it really didn't get larger, it stayed the same. And this dilation, this is not a dilation because it did not preserve the orientation, okay? So on the next problem, okay, on this next problem, yes, the angle measures are being preserved. The angle measures match, okay? This angle with that angle, this angle with that angle, they have the same measure. So, yes. And then did it preserve betweenness? Yes, you can see here that C is in between C prime and the point of center of dilation. So those three here are betweenness. Now let me show you what that looks like in green. So basically, if I were to add this measure with this measure, it gives me the larger measure. So the measure in the center is in between. All right, so I hope that helps you see it a little bit more. It did preserve betweenness. Now let's go talk about collinearity. Yes, they are all collinear. So C prime, C, and our center of dilation are all collinear. So let's check mark that. Is it preserving orientation? Yes, it is. My shape looks exactly in the same orientation as my original. And now let's talk about my scale factor. So you can use the center of dilation to help you find the scale factor. So if you go from C prime to the 0, and you also go from C to the 0, we have a measure of 4 over 2. So 4 over 2 becomes the number 2. And that's where the scale factor comes in. So our scale factor is 2. Is this transformation a dilation? Yes. And in fact, this dilation, since my K is greater than 1, or my K was 2, if I take the absolute value, it's greater than 1 because 2 is greater than 1. This is an enlargement. So that means we started off small and we got bigger. So we started off with the small triangle. Started off with a small triangle in the center, and our dilation, which is an enlargement, made it much larger. Okay, we finally have gotten to the homework, so let's try some homework problems. Okay, let's talk about number 2. Tell whether one figure appears to be a dilation of the other. All right, so let's check. The angle measures angles are congruent, right? So that part's fine. And the center of dilation somewhere in the center, and it would probably be collinear. Okay, so that part's okay. And between, right? It's in between, so there's betweenness. The ratio would be 1 to 1, and the ratios are equal. So this would be a dilation. So yes, dilation. Although it's not an enlargement or a reduction because the shapes seem to have stayed in the same size. So, all right, now let's go take a look at another problem. Let's go take a look at number 4. So you can see here is the scale factor of the dilation of triangle ABC equal to 1/2, and explain. Okay, so you want to try and see if you can find measures that are horizontal. Those are a lot easier to work with. So this measures a 3. And this measure 1, 2, 3, 4, 5, 6. So this is a 6. And we want to find out if the scale factor of triangle ABC equals to 1/2. So triangle ABC is my pre-image, and triangle A prime, B prime, C prime is my image. So this is what happened after we did our dilation. So we can see here that this is our original number, and this is our dilation. After the dilation happened, this is the bottom of the fraction. So this one goes first at the top, this one goes on the bottom. So we're going to write 3 over 6, and if we divide them both by 3, we end up with 1/2. So the answer is yes. The the scale factor is 1/2. Okay, make sure you're answering in a complete sentence. No half sentences, please. Okay. Okay, on number 6, you can tell that our scale factor is a 2. So since it's the absolute value is greater than 1, this is going to be an enlargement. So it's going to become larger. Okay, enlargement. And so you should end up with double the size of this shape. So if AC is this big, you should end up with double that for AB. And same thing for BC, you should end up with double the size for BC. Okay, so now it's A prime, B prime, C prime. All right, and that is our new one. Now for this here, the 1/3, since K is less than 1, then this is going to be a reduction. Now you work on the reduction. Of course, you have to divide by 3.